So thank you. As Bart said, I'm Tomer Ashur from KU Leuven. I'll present this paper by Archia Bar-On that was not able to attend due to personal reasons, and I apologize in advance that I'm going to read from my notes because of that. This work on improved higher order differential attacks on MISTY1 improves the best known cryptanalysis of MISTY1 using higher order differentials. This is done by showing that the previously known higher order differentials are not optimal and can be improved. The overview of the presentation is as follows. I start by presenting MISTY1. After that, I quickly recall what higher order differential cryptanalysis is and show how it can be used here. Then I move to presenting the previously known attacks, putting a special emphasis on attacks by Tsuno et al. After that, show the higher order differential used by them and how it can be considered as a set of smaller higher order differentials, and finally the attack. So MISTY1 is a block cipher designed by Mitsuru Matsui in 1997. It is one of the Japanese cryptrec e-government ciphers and has gained recognition outside Japan when it was selected for the European NESI recommended ciphers. It was also approved as an ISO standard in 2005. The block cipher Kazumi, which is used in 3G cellular networks, is a slight modification of this cipher, which makes it interesting for cryptanalysis. And this is how it looks like. So it has an 8-round Feistel structure, as you can see on the left part of the slide. The F function for this structure is in itself a Feistel construction of 3 rounds with, as an F function for that, another Feistel construction with S boxes of 9 and 7 bits. Starting from the first round, and after every 2 rounds, an FL function, this thing, is applied independently to each of the input halves. Since its introduction, it has received much cryptanalytic attention. The best attacks to date are a higher order differential attack on 6 rounds of MISTY1 with 4 of the 5 FL layers that requires 2 to the 49.4 chosen plaintexts with similar time complexity by Tsuno and others, and an impossible differential attack on 7 rounds with 3 out of the 5 FL layers that requires 2 to the 58 known plaintexts and 2 to the 124.4 time. A zero correlation linear attack on 7 rounds with 4 FL layers that requires 2 to the 62.9 known plaintexts and 2 to the 118 time. A higher order differential attack on 7 rounds with 4 out of the 5 FL layers that requires 2 to the 48.7 chosen plaintext and 2 to the 116.4 encryptions. A weak related key amplified boomerang attack on 7 rounds with 3 FL layers that requires 2 to the 54 adaptively chosen plaintext and ciphertext and 2 to the 55.3 encryptions by Lee and others. And the meet in the middle attack, which allows to speed up exhaustive search on the full cipher. This work contributes to these efforts in 3 ways. First, it shows that the 44th order differential characteristic for the 4-round MISTY1 can be replaced by a more efficient 43rd order differentials, which also reduce the data complexity and because of that also the time complexity. It also shows that by using the partial sums technique, the time complexity of the attack on 7 rounds of MISTY1 with 4 FL layers can be reduced by a factor of 2 to the 16. And it presents the first attack to a variant of the cipher with 7 rounds with all 5 FL layers that uses 2 to the 51.4 data and 2 to the 121 time. So before we talk about the higher order differential attack, we recall what higher order differential is. So higher order differential cryptanalysis was presented by Knudsen in 1994, and it's an extension of differential cryptanalysis where high order derivatives are used instead of just 2 messages. The messages are organized in a structure and XORed all together, and if the structures are built properly, the ciphertexts respective to the plaintext exhibit some behavior that can be used for a key recovery. So the previous attacks on MISTY1 are composed of a series of observations. The first one is that the 7th order differential covering 3 rounds of MISTY1 without any FL functions that is presented on this slide can be constructed like that. If we construct a structure of size 2 to the 7 messages that covers all possible values for bits 0 to 6 here, this division is of 7 bits and 9 bits. So if we iterate over all possible values for bits 0 to 6 and fix all others, we get that the ciphertext difference in bits 57 to 63 is 6D after 3 rounds, independently of the key. The next observation is that the FL layer can be bypassed by considering the same bits, and for each of them, what is called the neighboring bit. A neighboring bit for this cipher, for bit I, is just bit I plus 16. So if we consider a structure of size 2 to the 14 that goes over all values in bits 0 to 6 and 16 to 22, we can bypass the FL layer as we can see here. The next improvement is to consider the faster structure of the cipher by considering all 2 to the 32 possible values here. So on the right side, and this means that we have a structure of size 2 to the 46 that bypass the FL layer and goes for 4 rounds. And the last observation is that each of the 14th order differentials is in fact 28 12th order differentials, out of which 22 are linearly independent. This means that the data and time complexities of the attack based on this, on the 46th order differential can be improved by a factor of 22. So the results of this paper by Achia Bar-On are similar in nature. To find out if the 12th order differentials can be improved, they considered a version of MISTY1 without any FL layers and used an experimental approach to check if the order of the differentials can be reduced. So for each of the 12th order differentials, they checked all subsets of its bits to see whether it's also a higher order differential. And the result is that it is indeed. In each of the 22 12th order differentials, we can drop or fix 1 neighboring bit. So we have an 11th order, higher order differential that can improve the data complexity. And another thing they found out is that this number cannot be further reduced. So any subset of these bits is no longer a higher order differential. So given the set of 11th order differentials, now we somehow need to bypass the FL layer. It's given that the 12th order differential that we started with does pass the FL layer, specifically FL3, which I don't have a slide here for. And for each 12th order differential, we can write the 11th order differentials in 3 possible ways. So if we repeat the attack 3 times, writing the differentials differently, it's guaranteed that that the 11th order differential also bypass FL3. And if we want to exploit all possible 11th order differentials, we need to repeat the attack 3 to the 6 times. That covers 3 rounds of MISTY1. And this gives us 12 11th order differentials, 7 of which are linearly dependent out of each of the 12th order differentials we started with. So if we multiply that by 22, that's the number of 11th order differentials we have. And the same argument can be made for attacking 4 rounds of MISTY1 by reducing the 46th order differential into 154 differentials of order 43. This attack needs to be repeated 3 to the 7 times, but since the time complexity is dominated by encrypting so many plaintext, this doesn't change anything. So the key recovery part, that's not this slide yet. The key recovery part can be also improved by using the partial sums technique. Using the 11th order differentials, the adversary can divide the involved key bits into two groups of size 130 and 58, such that the first group only depends on bits 0 to 6 and 12 to 16, and the second group only depends on bits 7 to 15 and 13 to 21. And the observation here is that all the bits if all the bits in the set share the same ciphertext bits, their effect cancel each other, and we only need to, this allows to reduce the structure because we only need to consider those terms which appear an odd number of times. So overall, the data complexity for attacking MISTY1 with 3 FL layers requires 2 to the 47 chosen plaintext. In fact, it requires a bit less, but since we can't use structure which are smaller than 2 to the 46, we have to use it twice, which means we need to use 2 to the 47 chosen plaintext. This improves the attack, the previous attack, by a factor of 5 with data complexity, as I've said, and since the encryption dominates the time, the time complexity is also 2 to the 47 encryptions. Another contribution of this paper is attacking 7 rounds of MISTY1 with 4 FL layers. So it's similar. We ask for the encryption of structures of size 2 to the 46 with the expected output, then guess some key bits and absorb some other key bits into the equations, use partial sums here to reduce the size of the structure, then guess some more key bits, again use partial sums to reduce the size of the structure, and we repeat that until the last round is completely peeled off. The last attack is an attack on 7 rounds with 4 FL layers. Oh, sorry, no. Sorry. The data complexity of the previous attack is 2 to the 50.1 chosen plaintext, and the time complexity is 2 to the 100.4 full encryptions, which is an improvement to the time complexity by 2 to the 16 compared to the previous attack on this variant. The last attack is, again, similar. It attacks 7 rounds with 5 FL layers, and this is the first attack on this variant. Again, ask for the encryption of structures of size 2 to the 46. First, reduce the size of the structure by using relations between the values here and the values here. Then guess some key bits to peel off the last round. Use partial sums to reduce the size of the structure. Guess some key bits. Repeat until, again, the last round is peeled. The data complexity for this attack is 2 to the 51.45, and the time complexity is 2 to the 120 full encryption. And I already said it's the first attack on this variant. That would be all. Thank you for your attention.